Good afternoon, everyone. Hope you guys had a good lunch. Hopefully you're not going to fall asleep on me. I'll do my best to keep that from happening. As the slide here says, my name is Jerry D'Antonio. I work for a company called VHT, formerly Virtual Hold Technology, and we are an Erlang and Ruby shop out of Akron, Ohio. And again, as the slide says, I'm here to talk to you guys about concurrency. So yesterday, I was monitoring the tweets for the conference, and somebody sent out a tweet that I thought was very interesting. And it asked the question, it said something to the effect of, RubyConf should give me a reason why I want to use Ruby in 2014. Now, I assume, like the rest of you guys, I really love Ruby, and I think there's a million reasons why people would want to continue using Ruby in the future. Unfortunately, when the question comes to concurrency, selling Ruby is a little bit harder of a sell. All right? Now, I'm not talking here about interpreter issues. I'm not talking about the global interpreter lock. I'm not talking about any of that kind of stuff. I'm talking about abstractions. All right, let me give you a brief bit of history. Years ago, I used to work in banking systems, and we wrote highly performant, highly concurrent systems in C++. Now, if you've ever had to deal with concurrency in a language like C++, you realize that it is full of a lot of pain and agony. We would spawn a bunch of threads and use a bunch of low-level locking and other types of kernel-level objects to try and synchronize those threads, and it was very easy to get wrong. It was so easy to get wrong that we actually have whole categories of bugs named after common concurrency errors. Right? So like most people who do that work eventually had to get out of it because it's just too painful. Right? About 5, 6 years ago, I discovered Ruby. I've been using Ruby ever since, and I love Ruby. Unfortunately, the concurrency tools that Ruby provides to us are pretty much the same things that I was using 15 years ago in C++. We have thread.new, we have mutex, where we can call synchronize, and we do all this low-level stuff, which is every bit as painful. All right? Now, if you look at what's going on in other languages with respect to concurrency, today we have this thing called asynchronous concurrency. Okay? Rather than trying to create a bunch of different threads and place a bunch of locks on a bunch of things and get into a bunch of contention, instead, we send operations off onto different threads or different processes. They do their thing, and then we coordinate those. Right? And if you look around a lot of the languages not called Ruby, you see a lot of really cool things going on. Right? Languages like Erlang and Clojure and Scala and even JavaScript and Java and C# are doing some very interesting things with respect to concurrency. Now, Ruby, being the great language it is, we can actually use these same abstractions in Ruby if we take the time to build them. Okay? They don't exist in our standard library right now. They don't exist in the language itself, but we can still build them and we can still use them. So my goal today is to give you a survey of some of the asynchronous concurrency techniques that are being used in other languages and show you how you can use those in Ruby today. This is going to be an incredibly code-heavy presentation. All right? Pretty much every slide in here is either a picture or code. Right? Now, there's a lot of stuff to cover, and I'm not able to go over everything in detail. So my goal here is all of this presentation in its entirety with extensive notes and all of the source code examples are up on GitHub. So you can go out there, you can clone the repo, you can pull this down, you can run all the code I'm going to show you. So as I go through this, I'm going to ask that you focus on the concepts that we're going to talk about. Because these concepts are things that are independent of any particular programming languages, and they are concepts that allow you that once you understand them, to start thinking about your code differently and start solving problems differently. And so that's really my hope, is that after you leave here today, you'll have some new ways that you can think about code in terms of concurrency, and you'll have an interest in going out and starting to write more concurrent code. Okay? Most of the code we're going to look at today is going to be from a gem that I put together called Concurrent Ruby. It's MIT licensed, open source, available on GitHub. It's something that we use at VHT today because we had some very specific needs we wanted to fulfill. Now, I'm going to show you that gem because it's the one I know the best, but it is by no means the best or canonical or right way to do anything. These concepts, like I said, are concepts that are independent of any language and can be implemented in many different ways. I'm just going to show you one possible way to use these particular ideas within Ruby. All right. So that being said, let's go ahead and move forward. In order to do this, we're going to need a crash test dummy. All right? When writing code examples of concurrent code, oftentimes we throw in these random sleep statements, and we say, something important happened here. All right? That's kind of fake when we do that. It sort of gets the point across, but it's not really a good example. So for this presentation, I created a class that we're going to use as our crash test dummy in most of the examples that we're going to go over today. And I put this class together on purpose, not as to show good object-oriented design, because it's really a crappy design, But this class will express a couple of ideas that are very important to us when writing concurrent code. So let me show you the crash test dummy we're going to use. Okay? This is a very simple class. It does one simple thing. When you create this, an instance of this, you're going to pass the name of a company in. Yahoo, Microsoft, Apple, Google, whatever. When you call update on this, it's going to go out to this Yahoo API. It's going to retrieve information about what ticker symbols that company trades at on different stock exchanges around the world. That data is going to come back with some Ajaxy wrapper stuff around it. So we're going to strip that off, and then we're going to update this internal member variable with that data. Now, here's a couple things to keep in mind. How many people here have heard that shared mutable data is bad? All right. Whatever you were told is a lie. It is 10 times worse than that. Right? Shared mutable data in concurrent programming is really bad. This thing is fat with shared mutable data. All right, first, this thing goes out and it performs blocking I/O. All right, that's good for us with respect to concurrency because blocking I/O is one reason why we'd want to write concurrent code. But it then goes and the object itself mutates when we go and we update it, which means now this thing, if we share it across the threads, is shared mutable data. Even worse, this has an internal member variable, which is an array of hashes, which we expose through an attribute reader, which means we now are passing a reference to a mutable object outside of this thing, potentially across threads. So this thing is very, very dangerous, and that's why we're going to use this as our example, because we're going to show different ways that we can use this thing in a concurrent environment and hopefully not keep ourselves up late trying to debug all kinds of weird bugs. So with that, let's talk about the first concurrency object that we're going to look at. This is called the future. How many people have heard of futures in terms of asynchronous concurrency? Cool. A future is a general term to describe any particular operation that gets started and returns a result at some point in the future. Okay, so it's a class of different types of asynchronous concurrency objects. Future also, very specifically, is one of the two core concurrency abstractions in the Clojure programming language. For those of you who are not familiar with Clojure, it's a Lisp-like language that runs in the JVM, which was designed specifically to be concurrency friendly. So here's how a future works. It's very simple. It's probably the simplest and most pure asynchronous concurrency abstraction. Here's how it works. You create a future, and you give it some operation. At that point, the runtime schedules that operation as soon as possible. Okay? A future has three states. It can be pending, which is what happens on creation. It's not done yet. Once the operation completes, it can be either fulfilled or rejected. Okay? If the operation completes successfully, it becomes fulfilled. If the operation throws an exception, that exception gets swallowed, and the state becomes rejected. At that point, you can then retrieve either the value, if it was a successful operation, or you can retrieve the reason for the rejection, which would be the exception that was thrown. So very simple, very straightforward. You basically throw this thing off on another thread, let the runtime schedule it, do important stuff, and then later on you come back and you ask, what was the result of that operation? And if it blows up, your program doesn't blow up. It just tells you that your operation blew up. So it's great. It's very simple, and it's a very easy way to start adding concurrency to your programs. Now, how many people are JavaScript programmers here? All right? So you guys are all familiar with callbacks, right? Whenever you're dealing with asynchronous concurrency, there are two ways that you can retrieve the result of the asynchronous operation. One, as we see here, is query the object and say what happened. The other way is to attach a callback. Right? This is the JavaScript way of doing things, we attach callbacks. Ruby, it turns out, has a very serviceable callback mechanism built into the standard library. How many people here have heard of the observable module? All right? There you go. The observable module, which we know is based upon the gang of four pattern observer, actually can work as a very fine callback mechanism for any kind of asynchronous object. So in this particular library, I've tried to make it as consistent as possible and dependent only on the Ruby standard library. So in this case, this future class implementation is observable. So you can attach an observer to that, and then when the operation completes, the observer will be called. It'll be given the time that the operation finished. It'll be given the value of the operation or the exception that was thrown. Very simple. Now, I want to take a step away from future for a second and talk about a very important concept that is not unique to future but applies to all asynchronous concurrency. All right? There is a code smell on this screen. All right? And I'll even give you a hint of where it's at. It is up here on line 18. That is a code smell. Think about it for a second, and I'll give you the answer to what it is. All right? All advanced asynchronous concurrency abstractions try as much as possible to hide the details of concurrency from us. They try and hide the locking and the threading and all this other stuff that has to go on. But what we cannot do is change the actual nature of concurrent operations. And when we're dealing with concurrency, the order of operations is non-deterministic. Okay? Hopefully you've heard that term before. It's non-deterministic. We cannot guarantee at what order things happen. So line 18 right here, which looks fairly innocuous, is very interesting because once we create this future on line 17, that block is scheduled for operation, and we have no control over when that thing occurs with respect to anything else. So it is theoretically possible that that operation could complete before we add the observer on line 18. Okay? That's this nature of non-determinism. Okay? Now, in this particular case, all right, this particular future implementation is aware of that, and the addObserver method here behaves in a way that you would expect it to, despite that non-determinism. But the takeaway from this, and this will apply to everything we talk about today, is concurrency is non-deterministic, and that can never change. So always, when using these concurrent abstractions in any language, keep that non-determinism in mind. Okay, so that's a future. We're going to refer back to this a lot because you're going to see the API of this future several times. Let's talk about another very interesting abstraction that comes out of Clojure. Let's talk about the agent. All right. Clojure has two core concurrency abstractions, future and agent. All right. Clojure is the only language I know of that does something like agent. It's very fascinating. This is why I like to talk about it. I'll give you an example. Let's say you're writing a video game, and that video game, it's an old school arcade style video game, and there's a score. All right. And you've got all kinds of threads running around doing different things, and each one of those threads wants to update the score. Okay, and the way we would do that in the old school days is we would then put some kind of lock around that score. And every thread that wanted to change the score would have to obtain that lock, and it would have to block until it got that lock, and then it would update the score. So what happens is we have all these threads that we want to be doing these different things, but every time they have to update the score, they have to block and go into contention with one another. It's very inefficient. Right? So the agent from Clojure turns that on its head and says, rather than putting the lock on the value that we want to change, let's instead queue up the operations against that value and do it sans locking. So here's how the agent works. Right? Again, it's really fascinating. Create an agent, you give an initial value. Okay, value can be anything. In the score example, it would be like 0. Okay, then when a thread wants to change that value, rather than getting the current value, instead it throws an operation at the agent, which is running on its own thread, and it says, perform this operation against that value. The agent itself then queues up all of these different operations, runs them one at a time in order, so there's no contention amongst those operations. When that operation runs, it has complete access to that value. Another great thing about this is that the operation we're sending doesn't have to have a priori knowledge of what the value is. When that block runs, the agent gives the block the current value, and the block returns what the new value is. Right? And much like many of the things in this library, this particular implementation of agent also supports the observable interface. So we can hang an observer off of this. So now let's go back to that video game score example. In that case, every thread, we create an agent, set its initial value to 0, and every thread that wants to then update the score can throw a block operation at that agent. At any point in time, anything can retrieve the value of the agent. That retrieval, though, will get you the value at that time, irrespective of things that are still queued up. Right? But we then can hang an observer off of that and make it the observer's responsibility to update the score on the screen. And now we can take that video game score type scenario, and we can run that using an agent with absolutely 0 locking and 0 blocking of our worker threads. Okay, it's a very fascinating approach. Like I said, the idea for this comes from the language Clojure. Now, again, I'm going to take a step aside. We took a step aside a minute ago and talked about non-determinism. We need to take a step aside and talk about another concept that's very important in concurrent programming. This code right here is horribly, horribly broken. Right? The agent does exactly what it's supposed to do, but the way I use the agent in this code is ridiculously broken and bad. Take a second to look at it and think about it, and I'll tell you what the problem is. Okay? And I gave you a hint earlier on. During the introduction, I said there's something that we really need to worry about that's really, really, really bad, and that's mutation. Okay? The value that we gave to that agent is an array, right? And that is an array of hashes. And those are mutable data structures. So whenever we retrieve the value from that agent, we're retrieving a reference to a mutable data structure. So although that agent will queue up those operations on one thread to make sure they don't compete with one another, any thread that has a handle to that agent and wants to get that value is going to be retrieving a mutable reference. All right? And that's really bad. That can lead to a lot of pain and agony. Don't do that. So here's the question. How do we avoid doing that? Because let's be honest, we're working in Ruby. All right? A lot of the languages that are concurrency friendly are things like Clojure and Erlang and Haskell that have immutable variables. Ruby does not have immutable variables. That's a problem. So how do we solve this problem? In this case, we're going to solve it with a hamster. All right. Did anybody see that coming? All right. In 2000, a gentleman named Phil Bagwell started doing some research at something called a trie. All right. A trie is a high-performance tree-like data structure in which every node has at least 256 other nodes hanging off of it. By having 256 nodes off of every node, we can have 1 million nodes in a trie with only 3 levels deep, which gives us incredibly fast access to those nodes. He then followed that up with something called an ideal hash tree. Has anybody heard of an ideal hash tree? All right, ideal hash tree is a very high-performance data structure which allows you to create immutable data structures, but have them perform very fast because what you're doing is in the tree you're storing indexes to the objects you're not. And when you copy things, you're now copying the indexes, not the objects themselves. An ideal hash tree is the underlying engine that makes Clojure work. Clojure gets its immutable variables with high-performance list comprehensions because the underlying engine is this thing called an ideal hash tree. Well, fortunately for us, a couple of Rubyists went and read the same papers by Phil Bagwell and had the same ideas, and they created a library for us that provides us with high-performance immutable data structures, and that particular library is called Hamster. Okay? Hamster is an open source gem. It provides us with thread-safe, immutable, high-performance data structures. So now what we've done in this case is we replaced that example of the agent that we used before, getting rid of the array, which is not safe, putting in there a hamster vector instead. Now every time we operate on that vector, we of course have to replace the vector because it's a non-mutable immutable data structure. But really all we're doing is internally just replacing the indexing, and it's doing extremely fast. So now we've created a thread-safe, immutable data structure inside of our agent, and now we get the behavior that we wanted with absolute and complete safety. Okay? So the important thing to understand is in Ruby, we have mutable variables. Mutable variables are bad in concurrency, so when you are using passing variables across threads, make sure you, whenever possible, make them immutable. Now, the second example is an important one for comparison. This second example is from a library called ThreadSafe. It's written by one of the people from the JRuby core team, and it provides thread-safe implementations of Ruby's hash and array. It is a really great library that does really great work, and it's something that you should definitely know about if you're doing concurrent code, because thread safety is important. But notice, with that, we still have the same problem we had before, because it's still mutable. Okay? We're still passing a mutable reference. So you definitely should get to know thread safe. You definitely should get to know Hamster. You should definitely be aware of thread safety, but remember, whenever possible, immutability is the best. So those JavaScript programmers. How many JavaScript programmers in here are familiar with promises? All right. So a promise is a contract between you and something that happens on another thread. A promise is a very popular data structure, concurrency abstraction in JavaScript, and it's defined by 2 specifications, promises A and promises A+. A promise is basically a future, right? It's part of that general class of future. We send this thing off, and with the promises to us that it will get us a value at some point. Promises as expressed in JavaScript are very different than the future that we saw earlier in one special way. Promises are chainable. Okay? The future we looked at earlier was a one-shot deal. You send it out there, it does its thing, it returns a value, and it becomes immutable at that point. Done. Promises are chainable. A promise can beget a promise, can beget a promise, can beget a promise. They're not only chainable, that you can make trees out of them as well. Okay? In order to make that work, there are some error handling semantics built on there too. You can say, when this happens, rescue this, on error this, and so on and so forth. So a promise is very much like a future. In this implementation, A promise supports all of the same methods we saw earlier on future, the idea of state being pending, fulfilled, rejected, value, reason, and so forth. The difference is, however, is the chainability of this. There's greater internal complexity to make that happen, but you can then use that in very similar ways, just deeper chaining. In this particular case, promise does not implement observable. And the reason why is that in this case, the callback mechanism is built into promise through the chaining. Right? So promise, like I said, this particular implementation is very true to the promises A and A+ specifications from JavaScript, but it's a Ruby-ish library. OK. How many people here know what cron is? That should be everybody in the room. So one of the things that we oftentimes want to do is we want to have a task or something that occurs at a very specific time. If you're in Rails land, there are gems that allow us to do this. Right? But if you're outside of Rails land, not quite so easy. So looking at Java, of all languages, Java provides us with a really cool abstraction that allows us to handle this thing where we want to have something happen at a certain time. Now, of course, because it's Java, it has a really stupid name. It's called the Scheduled Executor Service. Right? But it's actually a really cool abstraction. And so because I'm not a Java person, I'm going to call it scheduled task. Okay? So this implementation of scheduled task is based upon Java's Scheduled Executive Service, and it does basically the same thing. You create this thing, you pass it a block, and you say, I want this operation to occur at a certain time, right? And then you can say either this many seconds from now or at this specific time, right? And then it just goes off and it does that, right? This supports the same for consistency, supports the same kind of interface that we saw in future earlier, because I'm not that smart and I like things to work the same, so I can remember them. So it provides us with the states pending and fulfilled and rejected and provides us value and reason and so forth. And this will then go and make that operation occur at a specific time. Now, the astute among you might be saying, all right, Jerry, that's really cool, but how is that different from just basically creating a future and making the thing go to sleep, right, when you first create it? Well, it really isn't. I mean, I could literally do the same thing by creating a future and having the first line of the block that I pass the future be sleep. There's two reasons why I don't. One is cancelability. Right? The intent of a future is to say, go and do this right now. The intent of a scheduled task is go and do this later. So a scheduled task can be canceled. You can't cancel a future. I mean, once you set that thing in motion, it's done, right? It's going to go and work. This allows us to cancel it. But there's another reason. It's more important. And again, this is something that it transcends this particular implementation, but is true of concurrency abstractions in general. Okay? And it's the idea of intent. Right? You'll notice as we've gone through this that we've worked very hard to decouple our business logic from our concurrency logic. It's done on purpose, right? If you've ever tried to test concurrent business logic, you found out that it's probably very hard and painful, all right? When we test, we set things at a known state, we change that state and verify that the new state is what it's supposed to be. Concurrency is non-deterministic. It is very hard in a concurrent environment to create a known state. That's the whole problem. So if you decouple your business logic from your concurrency logic, you can test the business logic in a way that's not concurrent, make sure that your business logic does exactly what it's supposed to do, our crash test dummy example being that, make sure it does what it's supposed to do. Then you can take a concurrency abstraction that is tested and that has defined behavior and does a specific thing, and you can put the two together with a very minimal intersection, and now your testing of concurrency becomes minimal because you just have to test an intersection, right? So when we do that, now we have code that very clearly expresses intent. When I'm looking at code and you see something that says scheduled task, that expresses intent. It has meaning. It tells you that there's certain concurrent behavior going on. If you see something called future, that expresses intent. If you see something called agent, that expresses intent. So although in this case we could have simulated scheduled task with future, or in fact we could have simulated all these things with something called actor we're going to look at later on, by having an abstraction that does one thing very well, we better express intent, and we allow ourselves to optimize that abstraction for the thing it needs to do. So scheduled task, in this case, looks very much like future, but it has that scheduling. Now, for all of us who like to use cron, and also in this particular case, this implementation of scheduled task does, of course, support observer as well, so that we can have that callback type ability, right? Again, I'm not very bright. I like my things to work consistently so I can remember how they go, so this is observable as well. So getting back to that cron example, we know that another reason to use cron is repetition. We want something to happen over and over and over and over again, whether it's every 5 seconds or every minute or every 10 minutes or whatever, Okay? Java provides us with a really cool abstraction to do that too. And unlike scheduled executor service, the abstraction for this in Java actually has a name that's not entirely stupid. It's called a timer task. All right? So a timer task is simply this. It says, here's an operation I want you to perform. I want it to perform at this particular interval, 5 seconds, however many seconds, right? And if that task takes longer than a certain timeout value, kill it. Obviously, it's broken, okay? You notice, though, one thing different about this than the things we saw before is this has a run method that we're calling on here on line 9. Remember that, 'cause I'm going to come back to that in a minute, okay? So we create this timer task. We give it the timer values. We send this thing off and say, just go do this thing over and over and over again, okay? Shouldn't surprise you by now that in this particular implementation, because we like consistency, it also supports observability as well, okay? So we can have this timer task go, we can run it, we can attach an observer to it, and every time that it occurs, we can then have the observer or observers respond to that in a callback-like fashion, okay? Now, so one of the things that this does, one of my coworkers is using this in a project he's working on, and came to me and said, how do I stop this thing once it's started? I'm like, what do you mean? It's supposed to go forever. You can call stop on it, but you call that. He's like, but I don't want. He said, I don't want to call stop from the main thread. He said, what happens if within the block that's running, there's something occurs, and I want to, based upon that logic, change the execution interval, or I want to shut this thing down? I said, well, it's a good use case I hadn't thought of, but it's a very smart one. So based upon that, him and I sat down, we paired, and we created small changes. And we said, you know what? Let's just, inside that block, every time it executes, let's pass a reference to the task itself. Basically, self, right? Within the block, self isn't going to be what we want it to be, so we'll pass that task in. Now, that scheduled task has the ability to change its own life cycle within the block by changing its own timer values or by making or stopping itself if necessary. Okay. Now, last, a really important topic we're going to talk about, well, not the last topic, but really a big topic. Let me ask this question. How many people have heard of the actor model for concurrency? Okay, good. How many people have heard? So, Always Sunny in Philadelphia, for those of you who don't know. How many people here have heard that Erlang implements the actor model for concurrency? All right. So actor model is sort of a big deal these days. Now, here's an interesting. Now, I've been doing this a long time, nearly 20 years. There's one thing I've learned in 20 years of being a programmer, is if there's anything that programmers want to talk about, apparently it's also worth getting into ridiculous flame wars over. And the actor model for concurrency is the same thing. Okay? This is surprisingly controversial in some circles. Okay? There are some people who think that the actor model is the only way to do concurrency and everything else should just go away. And there are people who think that they're completely wrong. Right? Not going to wade into that debate. Just understand that debate exists. There's also a debate about what exactly an actor is. So here's the thing. The actor model was first proposed in 1973. All right? A gentleman named Carl Hewitt and his associates working at the MIT Artificial Intelligence Lab published a paper called the Actor Model for Concurrency. Well, it shouldn't surprise you that in the past 40 years, a lot has changed with respect to programming. What they really described in this paper was a pattern. Right? We weren't using the term pattern the same way back then, so they don't call it a pattern, but they said, we've seen a bunch of things that behave a certain way, and we're going to document the way these things behave. And anything that behaves this way, we're going to retroactively call an actor. Right? This is also before the days of object orientation, long before Gang of Four wrote their books, so we didn't have great diagramming techniques for creating class and object designs. So they used the only notation that they knew at the time, which was a very mathematical notation. Which means this paper, which is very fascinating to read, has very limited direct applicability to today. The ideas 40 years later are still very good, but the paper, as far as being a blueprint for creating an actor, is very limited. So as a result, today in 2013, there is no single, universally agreed upon, strict definition of what an actor is. Additionally, there is no one canonical implementation of actor. If you look at everything that claims to be an actor and things that people claim are actors, even when they don't claim to be actors themselves, they all look very, very different. And so that leads to a lot of debate within the actor community about what really an actor should look like. Okay. So for the purposes of this presentation, I'm going to give you my definition of actor. Okay, I'm sure I'm going to get flamed for it by somebody, but we have to move forward. So here's my definition of actor. An actor is an independent, single-purpose, concurrent, computational entity. Say that again, independent, single-purpose, concurrent, computational entity that communicates via messages, okay? It's got to do something. It's got to be an independent computational entity that does something. A class called actor is not an actor. A class called actor can create an object which behaves as an actor, but it's got to be something that does something. It has to be concurrent, right? That was one of the key things about the original paper. And it has to be single purpose. Now, this is critical. When Hewitt and his colleagues wrote this paper, their example were people performing a play on a stage. Every actor fulfills a role. Every actor plays that role. There is not a tremendous amount of, there's no overriding control of those actors. They are all acting independently, but they coordinate amongst themselves to do something greater than the sum of its parts. So an actor must perform a role in order to be an actor. Okay? And one of the key things about the original Hewitt paper was it said you must communicate via messages. Okay? Now, they didn't define what a message is, and that's one of the areas where there's a lot of contention these days is what constitutes a message. Now, if you are using Erlang or you're using Scala or some language like that, they have built-in inter-process messaging systems, right? The bang operator in Erlang is a way of one process sending a message to another process. A message in that case is pretty cut and dry. In Ruby, we have no similar underlying communication mechanism to define a message. Therefore, in Ruby, it's kind of hard to decide what constitutes a message. So the example I'm going to show you is the example I like the best. It is by no means the right example or the canonical example, and I'm sure a lot of people will think that my choice is not good, and that's fine. But the example I'm going to show you is based upon Scala's actor class trait, from the Scala standard library. Now, Scala has since deprecated this particular trait and moved on to the Akka library. But this particular implementation of actor from Scala served Scala programmers very well for a number of years. And it exhibits all of the things that an actor is supposed to exhibit. And it's also very simple. And I'm a simple guy. I like simple libraries that are loosely coupled and that give me things that work really well by themselves. So here's how this works. Straightforward. You extend the actor class. The actor class then gives your object all of the message passing semantics it needs. It gives it the threading it needs so this thing can run on its own thread, right? And it handles queuing of the messages. Every time a message comes in, it calls the act method, which you, in your subclass, override in order to give your actor some behavior. All right? So in this case, this is a pretty simple example. All it's going to do is basically echo the message to the screen. Okay? Straightforward, very simple. Now, the problem with that, when you give each actor its own thread, or its own process, the problem you run into is one of contention, blocking. Right? If your actor performs some lengthy operation, such as blocking I/O, you run the risk of having a whole bunch of stuff back up in the queue. So most actor implementations will give you some ability to pull actors off of some shared mailbox, right? So that way you can have a whole bunch of threads running with a whole bunch of different actors, and you can send messages to one place, okay? F# mailbox processor works this way. Akka works this way. Scala's original actor works this way. Celluloid works this way, right? The idea of a pool. So the way you get a pool out of this particular implementation is you just call the pool method off of the class, tell it how many things you want, and it will return a whole bunch of actors that all share one mailbox and return the mailbox, right? It's very simple. You can then run each of those things in the pool, and you can start sending messages at it, and all those things in the pool will then start handling those messages. Okay, it's very straightforward. Okay, and again, this is a very Scala-ish way of doing things. So now you'll notice that when you call post and you send the message in there, there's no way to then interact with that message or that result later on. Okay, that was by design in Scala's actor class, because the original actor model paper from 1973 said actors only interact with each other via messages. Okay? Now again, a lot's changed in 40 years, and that's not necessarily that efficient, so sometimes you want to have other ways to interact with that. So Scala, Martin Odersky being a very smart guy, decided to create other ways to interact with the actor. So here's two other ways that you can interact with this particular actor when sending messages. The first one is the post question mark. right? What that does is it sends a message to the actor, and it returns a future object. Okay, this is a very common paradigm in asynchronous programming where we send something off for processing and we get back a future. In this case, that future object behaves exactly the same as the future object we saw at the beginning. Pending, fulfilled, rejected, value, reason. Okay? So I send this thing off to the actor, I get my future object back, I go do my very important stuff, and then later on I query that object to see how it occurred. The second example is post-bang. All right? There are cases where you may want to use an actor in a synchronous capacity, but here's the problem. An actor is trying to queue up these operations so as to prevent lock, so we don't have to lock, so that we can have these happen one at a time. If we try and use an actor synchronously and asynchronously at the same time, we run the risk of breaking things very badly. So in a case where you might want to use this thing synchronously, and again, Scala provided the same capability, you're going to call this method post-bang, which will then block and wait for the operation to complete, thus imitating synchronous behavior. Now, the problem with that is when that occurs, there's no way of knowing what the result is other than the return value of the method. In this case, on success, this will return the result of the processing of the message, right? So in this particular case, this is one of the few places in this library you're going to see any kind of exceptions being raised, all right? If this thing times out, we're going to raise a timeout exception. If, for some reason, the message can't be queued, we're going to get a lifecycle exception. If our operation throws an exception, the actor will then handle that internally the way it handles all other exceptions, and then re-raise that exception out of this particular method, right? And that way allows us to treat this in a very synchronous way, but we're given a very strong warning that really what we're doing might not be quite the best way to do it, and we're going to get exceptions, so we're going to want to wrap that in a rescue block. Okay. And at this point, it should be no surprise to you that this particular actor implementation also supports observers, because it's very common in the case of actor frameworks to provide some sort of callback against messages being processed successfully. So here we leverage that observer again. And if you're familiar with actors, you know that the canonical actor example, the hello world of actors, is a ping pong example. So for completeness, here is a ping pong example using this particular actor implementation. I took that directly from the Scala tutorial on actors and rebuilt it using Ruby. Okay. So last concept. How many people here have heard about Erlang being a very fault-tolerant language? 9 nines availability in some cases. How many people would like to have their Ruby programs have 9 nines of uptime? That should be everybody in the room. There's nothing magic about Erlang. You probably have heard of the let it fail philosophy of Erlang. Right? There really, truly is nothing magical about Erlang in the language or the virtual machine itself. It's a great language and it does some really cool things, but the actual 9 nines fault tolerance comes from something called the supervisor. Right? How many people have heard of the supervisor in Erlang? Okay. This is such a powerful concept that you see supervisors all the time in concurrency libraries. You see supervisors in Akka, you see supervisors in Celluloid, you see supervisors all the time. So what is a supervisor? The idea in Erlang is when we create these processes, we send them out to do things, and if something goes wrong, we want to let them crash. Why do we let them crash? We let them crash because we don't want to have anything in some kind of intermediate state. Okay, if you're like me, you've probably programmed some kind of wrapper at some point in your life where you thought, I'm going to put this really great, simple OO wrapper around some whole bunch of complex stuff. And I've got connections and all these various things in there, and then one of those things blows up. Now I've got this mess, and I've got to dig through all this kind of crap and figure out what state is this thing in so I can get the broken pieces back where they need to be. Erlang says, no, don't do that. There's only 2 states, good or bad. If it's good, great. If it's not, you should just kill it and let it die. Right? That works only if there's a way to restart it. Right? This philosophy is really good because now it's very easy. It's very freeing. I say, all right, I've got this complex thing. Something blows up. I'm just going to kill everything. Right? But that depends upon having something that restarts it. And in Erlang, that's the supervisor. Okay? This right here is a functionally complete implementation of Erlang's supervisor module. Okay? The Erlang supervisor module provides a lot of really great capabilities. It provides something called restart strategies, which allows you to define when one thing dies, what do I do with the other things? It allows you to define child types that can be permanent, temporary, transient, and that has meanings. You can provide a sliding window of intervals. You can say, if we get X number of crashes within Y period of time, we're going to shut the whole thing down. And one of the best things about Erlang supervisor is something called supervisor trees. Supervisors can manage supervisors, which can manage other supervisors. So if you look at Erlang's documentation on how to build fault-tolerant systems, they discuss a bunch of various different tree structures. Okay? This particular implementation here is a functionally complete version of Erlang supervisor, and here's how it works. You can give this thing anything that supports 3 methods: a blocking run method, a runnable predicate method, or excuse me, a running predicate method, and a stop method. You can use that and then you use the run method to start it and the stop method to shut it down. That's why we looked at a couple things earlier that had that run method. So what we're doing in this case, we're going to create an actor. From the actor class, we're going to create a pool of actors. Right? We're going to create a couple timer tasks that have random intervals. We're going to create a supervisor. We're going to tell the supervisor, manage and monitor all of these things. Here, add worker, add worker, add worker. We then start the supervisor, and it runs. Right? And at that point, it starts up all of those things, and all of those things run, and they all do all the things they want to do, and the supervisor monitors them, and if any of them should crash, the supervisor will restart them based upon the restart strategy. And if you want, you can have supervisors monitor supervisors so that way, if something's wrong with the supervisor, it can restart that whole thing. Right? And thus, you can get a supervisor tree, and that is how languages like Erlang and libraries like Celluloid and Akka and so forth get their fault-tolerant abilities by using supervisors to manage those processes. Okay. Now, this is a really long presentation, and we don't have a lot of time, so I want to mention 2 of the libraries that are express some really cool ideas in terms of concurrency. And the first one is going to be something called EventMachine. EventMachine is based upon the reactor pattern. Right? Reactor pattern was first documented in 2000. We like EventMachine a lot at VHT. EventMachine is basically like Node.js for Ruby. Okay? Again, all these slides are going to be up at GitHub as well as all the code examples. And the other thing is Celluloid. Celluloid is a fairly well-known, fairly popular actor-based library written in Ruby. Right? It's got a good following. It's got a very good community. And the Celluloid library has the expressed interest in making it easy for you to add concurrency to your code. This right here is the original example we showed at the very beginning of our crash test dummy with one change. Up at the very top, you see include celluloid. That makes this object inherently asynchronous. It becomes something you can create actors from. Okay? The celluloid is a great library for making your job easy, but this particular implementation I'm showing you here is horribly broken because it violates a bunch of celluloid rules. Okay? Celluloid has a very tightly coupled and it's very powerful, but it's very tightly coupled, and it has a lot of complexity internally because it's providing a lot of auto magic in order to prevent you from harming yourself through concurrency. So when you look at the celluloid documentation, there's a page of gotchas which describe the idiomatic way in which you need to use celluloid. So celluloid is another very powerful library for doing actors and for doing supervisors. But using celluloid properly requires a little bit of work. So I encourage you to look not only at the library that I put together, but the EventMachine and also celluloid, but make sure when using each of those libraries that you're aware of the idiosyncrasies of those libraries and how they work. And remember, we can never escape the underlying realities of concurrency, which are non-determinism and shared immutable data. So with that, my final thought is this, right? My challenge to you is to go out and write code. Okay? If you've never written concurrent code before, you should know that writing good concurrent code is something that requires effort. You can't learn about it by reading. You have to do it. Concurrent systems don't behave the way non-concurrent systems work. They have different design patterns that make them work. They have different ways of testing and debugging, and the only way to learn this is to write the code. Over the past 45 minutes, we've looked at a tremendous amount of code that did a lot of very, very powerful things, and we never, ever once had to type thread.new. We never once had to type .synchronize off a mutex object. Okay? You can go out using the libraries that we've looked at today, using the code that I put up on GitHub, and you can write concurrent code. So if you think concurrency is important, which you should, if you think that learning to program concurrency is good for you at your job and your career, which you should, and if you think concurrency is something that is going to become just more important in the near future, which it is, then you need to go out and write code. So out on my GitHub page, all of the slides, detailed notes, all of the source code in RB files, and even a gem file. So that's my challenge to you. Pull out your computer, open up your favorite editor, git clone, bundle install, and write concurrent code. And with that, I'm out of time. Thank you very much. My name is Jerry D'Antonio.